So this is what we have seen, the variation of ionization potential along the period it increases and down the group it decreases. Along the period the increase is not gradual. Actually we cannot say that it is increasing in a particular systematic order. Actually there are ups and downs, but in general we can say that it increases along the period. But these ups and downs are because of the other factors other than the size of the atom. Not only the size determines the ionization potential, but also the electron distribution in the uh, electronic configuration. Say for example, the helium is found with 1s2 electronic configuration, which is actually when you move from hydrogen to helium, as per our usual discussion, hydrogen is with 1s1 electron and helium is with 1s2 electron. So another electron is added to the same subshell. Therefore, the distance between the nucleus and the outermost electron is not changing, but the Coulombic force of attraction increases. Therefore, helium supposed to be smaller than hydrogen. As the helium is smaller than hydrogen, the electron is closer to the nucleus in the case of helium, and hence the energy spent to remove the electron supposed to be higher for helium than that of hydrogen. That is what is the normal explanation. But when you actually measure the ionization potential of helium is found to be greater than hydrogen. The reason is exceptionally greater. The reason is it not only decreases in size, but the electronic configuration is also complete. But if you compare these two things, look here, beryllium and boron. See, beryllium is bigger, boron is smaller, but ionization energy for beryllium is greater, boron is smaller. The same reason. Here it is the completed electronic configuration. Here it is incomplete electronic configuration. And similarly, nitrogen and oxygen. Oxygen has a partially filled electronic configuration. Nitrogen is a half-filled electronic configuration. Because of its half-filled electronic configuration, it attains more stability. So the removal of one electron will lead the system from stable configuration to an unstable configuration. Hence, it is not willing to release that electron. Therefore, more amount of energy has to be spent to remove the electron, and hence it has the higher ionization energy, and this has the lower ionization energy. So these are all the various factors that we have discussed. And when you move down the group, the increase in the nuclear charge is observed, and increase in the atomic size is also observed. And apart from this, increase in the number of inner electrons is also observed. And the combined effect of all these three factors, the down the group ionization energy decreases. So if you take a cesium, the electron can be very easily removed. That is why the cesium metals oxides or the compounds of a cesium are used in the photovoltaic cell. You may be very familiar with what is a photocell. When a light falls on the cell, the electrons are ejected. Photoelectric effect, which is a phenomenon in which electrons are ejected from the polished metal surface when light energy of a suitable wavelength falls on the metal surface. This is photoelectric effect. You may be knowing the applications of a photoelectric effect. Anybody knows the application of a photoelectric effect? Any one or two applications? Just you can tell me if you know any application. Anybody? Anybody knows the application of a photoelectric effect? Nobody knows. Okay, right.
Sir,
Yeah, tell me.
radiusல change இருக்கும்.
Which one? Important concept, which is called electron affinity. we are going to see electron affinity. Electron affinity is the measure of a tendency of an atom to change into an anion. See, look here, watch carefully. I am taking a neutral gaseous atom and I am trying to add an electron to this atom so that an anion is formed. When an anion is formed, energy is given out. See, the difference between ionization potential and the electron affinity is this. In the case of ionization potential, I have taken a neutral atom and I supplied energy to remove the electron comes out. So their energy is supplied. Here energy is given out. So if energy coming out increases, that shows that the affinity for the electron is also high. And the electron affinity is expressed in terms of electron volt per atom or kilojoule per mole. So you can think of like this. Suppose a person is very hungry. He is in need of food. The electron is the food. If he is very badly hungry, he will be giving more money to get the electron to become an anion. If the tendency is less, this fellow is just less fond of the electron, then he will be giving only least energy. So if this atom is ready to absorb the electron even at the expenditure of large amount of energy, means that is the energy coming out, if it is of a very big quantity, that shows that the electron affinity is also very high. So it is also expressed in a different manner. It is the measure of tightness with which the atom binds an additional electron to itself. Suppose an electron is given, all the electrons in the atom are tightly bound with the nucleus. Now, it is the measure of a tightness that the nucleus can bind one more additional electron, not its own electron. When an extra electron is given, what is the tightness with which the nucleus is binding the extra electron? That measure is called electron affinity. But if you want to study the periodic trend of electron affinity, when you move from left to right, that is along the period, the electron affinity increases because the size decreases. As the size decreases, the additional electron will also go to a place where the orbit is closer to the nucleus. Therefore, a greater attraction is felt by the extra electron also. Therefore, the tendency to attract the additional electron is also high. Hence, along the period, the electron affinity increases. But down the group, electron affinity decreases because down the group, the atom itself is ready to lose its own electron. And what is the need for that atom to attract an extra electron? See, it is willing to donate even its own electron. Therefore, if you try to make the atom to have another additional electron, it will not show any attraction towards that electron because the effective nuclear charge also decreasing. It is also decreasing down the group. Hence, the electron affinity increases along the period and the electron affinity decreases down the group. And you know one thing, the metals are called electropositive elements, or the electropositive nature is to donate electrons. Any atom which is ready to donate electron are having electropositive character, and it is called the metallic character. So the metals have this fundamental character to lose electron. Therefore, for metals, the electron affinity is very less. For non-metals, the electron affinity is very high. So when you move from left to right in a periodic table, the metallic character decreases and the non-metallic character increases. And when you move down the group, the metallic character increases and the non-metallic character decreases. Therefore, that element which is found at the left bottom of the periodic table is highly metallic, and that metal which is at the right top of the periodic table will be highly non-metallic. That is why in the p block elements, if you draw a diagonal connecting the left top and the right bottom corners, if you draw a line, the elements which fall below the diagonal are metallic and above the diagonal are non-metallic, and the elements which fall on the diagonal are called metalloids. Metalloids means the elements which show both metallic and non-metallic characteristics. See, if you take the halogens, halogens are already having S2p5 electronic configuration. So this S2p5 electronic configuration is unstable because of its partial nature. So hence, when it gains one more electron, it will become S2p6, which is the electronic configuration of noble gases. So what happens? Halogens show very high electron affinity to form S2p6 electronic configuration. But when you take the halogens alone, so in the first point we have already said that halogens show very high tendency to have one electron extra so that they can attain the electronic configuration of a noble gas. But when you compare the electron affinity of the halogens themselves, see the halogens, when you move down the group, the normal trend of electron affinity down the group is observed. So chlorine is found to be of highest electron affinity, and less than that bromine, and the least among the halogens is iodine. Because down the group the same effect, the size decreases and the effective nuclear attraction decreases, therefore the atoms are becoming bigger and hence they show the least electron affinity and all that is there. But we have left fluorine here. We are not discussing the fluorine. If it is so, the fluorine is supposed to be the most electron, the element which shows the highest electron affinity. But actually among the halogens, chlorine shows the highest electron affinity, not the fluorine. Even though fluorine size is very small comparing chlorine, even though it is found at the top right corner of the periodic table, which is expected to be highly electron with a high electron affinity, it is found to be less, it shows less attraction to the electron than chlorine. See, the reason is fluorine, the electron affinity is unexpectedly low because of the very small size and also because of the high electron density in relatively compact 2p subshell, and the strong electron repulsion is there, which decreases the electron affinity. See, the atomic size is very small. In the small size, the 2p orbital is very compact. It is not able to accommodate the 5 electrons. And if you put one more electron, the 6th electron in the 2p subshell, what will happen? The nucleus attracting the extra electron and the electrons repelling themselves, and these two forces will compensate. Therefore, the electron repulsion predominates the extra electron nucleus attraction, and these things decrease the electron affinity. That is why fluorine, in spite of its very small size and in spite of its position in the periodic table, it shows a decreased electron affinity. So this point you should always remember. Why among the halogens, chlorine is having the highest electron affinity and the fluorine has unexpectedly low electron affinity. You should understand this reason behind this observation. Look at the electronic configuration. The S2p5 electronic configuration will show high electron affinity because the addition of one more electron will result in a stable electronic configuration. But the electronic configuration with the S2p6 will show very low electron affinity. Actually, it shows zero electron affinity. The electron affinity of a halogen, noble gases is nil. Actually, it is a zero. And also, it is a zero for, practically it is a zero for beryllium, magnesium, calcium, and nitrogen. Because beryllium has a completed electronic configuration and also small size and also relatively compact in its electronic arrangement, and the magnesium is also having a completed electronic configuration 3s2, and the calcium is also having a completed electronic configuration 4s2, and the nitrogen is having a half filled electronic configuration which is very stable. That is why even the ionization potential is high and the electron affinity is zero. So the elements with a fully filled electronic configuration or with a half filled electronic configuration, their electron affinity is practically zero. And also, if you look into the electron affinity along the period and down the group, you can see the irregularity in the quantities, in the measures. Why there is an irregularity? See, the electron affinity of beryllium is less than the electron affinity of lithium. But the size of beryllium is bigger than the size of the lithium. So there is a reversal order. Similarly, the nitrogen electron affinity is less. Oxygen electron affinity is greater. But if you look at the size, nitrogen is bigger than oxygen. But when you take the size into consideration, beryllium should be more electron affecting than lithium. Nitrogen has to be with more electron affinity than oxygen. But the electron affinity is of the reverse order, but the size is of the other order. The reason is the electronic configuration. Therefore, what you should understand, what the determining factor is not only the size, the other factors are also playing vital role. So the electronic configuration is also playing an important role in determining the electron affinity of the elements. So anything will make a contribution. But what is the overall effect? That is what we are concentrating. You should not say that it is the size alone determining electron affinity, or electronic configuration alone determines the electron affinity. See, electronic configuration of a fluorine favors electron affinity, and the size also favors electron affinity. But what happens? Because of the very small size, the electron repulsion dominates. So you have to look into all the various factors, and then finally you have to find out the overall effect of all these factors. That is how the science has to be understood. That is how any branch of the science has to be taken up. Say, for example, what are all the various reasons for the fidelity of a vehicle? When fidelity increases, stability decreases. When stability increases, fidelity decreases. You say the height. It is not only the height. You may say the size of the wheel. It is not only the size of the wheel. You may say it is the weight. It is not only the weight. It is all the overall weight of the height, the size of the wheel, the weight, everything. So there are certain vehicles which are with the smaller wheels, which are found to be more stable or less stable, because the other factor may increase its stability. So similarly here in the case of elements, it is not only the size, not only the electronic arrangement in the orbitals, it has so many other reasons. So we have to understand, putting all the reasons together, we have to conclude and we have to find out one common idea which will go in accordance with the experimental values. That is what is the idea behind the science. Now you see, as in the case of electronegativity, uh, as in the case of ionization potential, we have seen the first ionization potential and the second ionization potential and so on. And we have also shown that the first ionization potential is always less and the second ionization potential is higher, because we are trying to remove the electron from a system where already an electron is removed and which is positively charged now. Similarly, the successive electron affinities are also taken into consideration. Look here, the first electron affinity is positive. That means when one electron is added to a neutral system, the system releases energy. Hence, the first ionization energy is a positive. Look here, oxygen becoming oxygen minus. I have added one electron. Or even you can compare in this diagram. Oxygen gains an electron and becomes oxygen minus. The electron affinity is a plus 140.9 kilojoule per mole, which means that it is releasing 140.9 kilojoule of energy to become a negatively charged ion. When I try to add one more electron to the same system to make oxygen 2 minus, as this oxygen is already negatively charged, addition of another electron becomes very difficult, where I have to supply energy to add the electron. See, in the first case, it released energy. In the second case, I am supplying energy of a greater amount to add one more electron. That is why the electron affinity becomes negative here. See, in the endothermic and exothermic reactions in thermodynamics, you might have studied that if a process is found to be exothermic, energy is coming out. If a process is said to be endothermic, energy is given in. For exothermic processes, we put a minus sign for the delta H. For endothermic processes, we put a plus sign for the delta H. But here, in the first case, energy is coming out, but a plus sign is given. In the second case, energy is supplied. We give the energy, but minus sign is given. This sign is the sign of electron affinity. If the element shows electron affinity, it is given plus sign. If the element shows it is not ready to accept electron or it repels, then it is given minus sign. But thermodynamically, the enthalpy change is given the opposite sign, because in the first process, energy is given out. It is an exoergic process. Hence, the thermodynamic delta H value is minus 140.9 kilojoule per mole. But electron affinity is a plus 140.9, because the plus sign indicates the positive tendency of the element to absorb an electron. This negative sign indicates the negative tendency to absorb an electron. But the delta H calculated using the Born-Haber cycle, there is a cycle called the Born-Haber cycle, proves that the sign plus for endothermic process and minus for exothermic process, and the oxygen becoming oxygen minus is an exothermic process, and the oxygen minus becoming oxygen 2 minus is an endothermic process. Therefore, these signs you have to be very careful about. So, the next idea is electronegativity. Before electronegativity, I just disconnect the meeting and please get reconnected immediately. The 40 minutes is over.